to today's colloquium. We're very pleased to have Philip Hopkins here from Caltech. He's a professor of theoretical astrophysics. He got his bachelor's degree at Princeton and worked with Nettebekal on clusters. He then went on to Harvard and got his PhD with Lars Hernquist. This is a very impressive CV. I'm going to keep going through it. And went on to UC Berkeley as a Miller Fellow and then as an Einstein Fellow and worked with Elliott Poret. And the most impressive thing, oh, I forgot to mention some of your honors, Sloan, the Helen B. Warner Prize, NSF Career Award, but they all pale in comparison to the fact that he comes from Cleveland, Ohio. And Cleveland, Ohio has produced two world-class astrophysicists, theoretical astrophysicists, and both of them served time at Caltech. Mark Kamiankowski and Philip Hopkins. So Philip is going to tell us about feedback in dark matter. Are there actually small-scale challenges?
Thank you. Thanks for that introduction. Tom Prince would want me to mention that he's also from Cleveland. Apparently he's from like 5 minutes from my house, but he's not a theorist. So, I'm wearing a Cavs shirt, by the way, underneath this. No, it's great to be here. Sorry, it's a quick visit, but I'm sure I'll be back sometime relatively soon. So those of you that I didn't have a chance to talk to, I'm sure there will be other chances soon. And likewise, if you're in Southern California, please come visit. So I'm going to talk today about work that myself and a lot of collaborators have been doing as part of this project we're calling FIRE, for feedback in realistic environments, because even theorists need to come up with cheesy acronyms for our NSF proposals. This is a project primarily focused on understanding galaxy and star formation, but also the role of dark matter, basically trying to better understand the constraints on dark matter and the effects of different modified dark matter models that have been proposed, as well as just trying to understand star formation and galaxy formation for their own sake. We've been working on a lot of different projects in this area. There's a huge group of students and postdocs involved, so these are some of the postdocs who've been involved in the work I'm going to describe. Some, Andrew Wetzel and, Robin Sanderson have gone on or are going on to faculty jobs, and many of them still very involved in the project. I'll try and identify where they've really led the work as I describe it, and also a large number of graduate students involved as well. And not all of this is directed towards the work I'm going to describe today. There's a bunch of other stuff. Some of you have had a chance to talk about work we've been doing on things like dust in the interstellar medium or the stellar IMF or a lot of other problems. But again, since you don't want to hear me talk for 4 hours, I'll focus on the cosmological aspects of these simulations. So just to give some introduction, I want to set up the big picture, and I apologize if this is a little bit pedantic, but hopefully it's useful to remind everybody the context. So on the very largest scales, we want to ask how we go from sort of the Big Bang to the galaxies that we see today, spirals and elliptical galaxies, and we have our cosmological initial conditions. If you care about the low redshift universe and galaxy formation, and you can treat the universe as of the CMB as initial conditions. We don't need to know what happened before then, we just need to be able to describe the universe at that point. We can describe statistically the density fluctuations, and we have a concordance cosmological model that describes the ingredients that we need to evolve from those initial conditions. So to first order, you add gravity and go. So this is an example from Volker Springel of a simulation doing just that, literally just that, just gravity. So it's just the standard cosmological expansion history. Dark energy enters, but only insofar as it provides an additional term in the expansion in the Friedmann equations, and then everything's just matter that's obeying gravity. And so we have the usual, linear fluctuation. Small fluctuations grow linearly in the high redshift universe. They turn around and collapse into the cosmic web, and then ultimately large-scale dark matter halos form. These collapsed, virialized dark matter objects collapse under their self-gravity, and they drag the baryons with them, and those will be the seeds for galaxy formation. And in case it wasn't obvious, this movie is in co-moving units. We just factored out the expansion of the universe. So you just see everything turn around and fall. this is a fly-through of that. You can compare that to observations, and that's not what this talk is going to be about, but I think most of us are well aware that this very simple model works fantastically well on large scales. Basically, to a few percent, we can, of course, have very interesting discussions about H naught from the CMB versus supernovae, but at least to the few percent level, this really works remarkably well describing all the large-scale cosmological data. This is one example about the large-scale matter distribution, comparing mock redshift surveys from simulations to real redshift surveys, and by eye, you can't tell the difference. More importantly, quantitatively, more or less every metric we've been able to throw at these can't tell the difference between the statistical distributions of matter. And what this tells you, basically what you need to satisfy the large-scale constraints is that your dark matter needs to obey the following conditions. It needs to act like, whatever it is, it needs to act like something that's pressure-free or collisionless relative to the standard model. It doesn't mean there can't be any collisions or interactions. It has to be very weak compared to most standard model interactions. It has to be non-relativistic, at least in the bulk. You can actually have ultralight bosons, for example, but if you want to play that game, you have to do tricks like make them into a Bose-Einstein condensate so that the group velocity is non-relativistic. So they're non-relativistic in the bulk. And it has to be weakly interacting with a lowercase w, not an uppercase w, meaning that just any interaction outside of gravity is not very strong. And that's basically what you need the dark matter to do on large scales. And I think we're all familiar with that. But within those bounds, you could look at smaller scales if you wanted, but of course in order to go much smaller than those scales, you need to account for the fact that the baryons get much denser than the dark matter and can dominate or affect small-scale structure. So okay, let's track the baryons. So we throw in the baryons, we say, okay, on large scales it acts like a fluid. We know how to do fluid dynamics. It needs some chemistry because we need to account for the fact that gas can do things like get ionized and then recombine and radiate energy away that escapes, so it cools, but we know how to do that. And this leads to the standard picture of galaxy formation in a CDM universe that's been around since the 70s, where basically dark matter halo drags the gas with it, because the dark matter is most of the mass. It undergoes a shock during the virialization of the halo, gets shock heated up to the virial temperature, but then it can cool. It radiates its energy away, vaguely conserving angular momentum, which means it cools into a flattened disk. And voila, you have Milky Way. And then you iterate the process inside the galaxy, where little clumps are gravitationally unstable, collapse into GMCs, down to stars and planets. And astrophysics is solved from all the top scales all the way down to the bottom. And that's the range of scales that we're interested in these simulations. Of course, this is a tremendous range of scales, so even doing this from the top down would be quite an achievement, and we break the problem up into smaller scales, where we sort of use the big scale simulation as our initial or boundary conditions for the next smallest scale simulation. But if we just stopped at the physics I just described, we would get everything terribly, horribly wrong. Because all I've done is included fluid dynamics and gravity and chemistry, cooling of the gas. And if you do that, the predictions are very simple and very robust, and they're very wrong. And this is one example. This is the predicted mass function of galaxies, stellar mass function. And the white line is what we observe at redshift 0. The cyan line is what this toy model gets you. The shape of this line is robust because it's basically what you get if you convert all the baryons in the universe into stars. Every halo drags its baryonic mass in, and what you get is for almost all halos, except for a few out here, the cooling time of that gas is much shorter than its dynamical time, and it's self-gravitating, which means it collapses under its self-gravity in a dynamical time, maybe a couple dynamical times, but that's much shorter than the Hubble time. So it'll inevitably collapse, and I'm just going to assume that at some infinitely high density, cosmologically speaking, it'll eventually turn into stars. And if I zoom in more detail, it gets even worse, because actually what I predict is that all the stars are in globular clusters, and all the stars are really brown dwarfs, or super Jupiters, basically. They're not even solar mass objects. Another way of phrasing the mass function problem is just in terms of the fraction of baryons that turn into stars, as I described. This is from Ben Moser, but just comparing what fraction of the baryons basically have turned into stars as a function of the parent dark matter halo mass. This is done from just matching the mass function, but there's a wide variety of constraints. You can use lensing or kinematics to estimate halo masses, and these all give more or less consistent answers. So the peak of this efficiency of baryons being turned into stars happens right around the mass of the Milky Way. That's where this peak is. A halo mass of about 10 to 12 solar masses. But even at that peak, the universe only turned maybe 20% of the baryons it had available in the halo into stars. And it drops like a rocket lower and higher masses. And I show this plot, I think most people are aware of this, but I show it to emphasize that especially at low masses, this is not a factor of 2 in the details kind of problem. This is a multiple orders of magnitude discrepancy. So there's clearly just fundamentally missing physics here, one way or another. Another signature that's very closely related, that relates this to the old questions about dark matter, is the missing satellites problem. So if you take dark matter that obeys those simple assumptions, then you simulate the dark matter around an object the mass of the Milky Way, you get something that looks like this. This is one of Andre's old simulations, where there's tons of substructure. And cold dark matter is basically self-similar, which means that a Milky Way, if I showed you, coma in the dark matter, you wouldn't, by eye, be able to guess the difference between coma and the Milky Way. Even though we can count a huge number of satellite galaxies in coma, and we can count a couple dozen around the Milky Way. So what's going on? We've convinced ourselves, this is an older map from the HEA, but there's newer ones, and we've convinced ourselves that it's not just that there's tons of satellites out there that we haven't found observationally. We're pretty complete down to at least the mass range where there's a huge discrepancy with the number of dark objects here. So why don't we see thousands of satellites around the Milky Way? This is the missing satellites problem. Moreover, if you look at any of those satellites in detail, other discrepancies start to pop up that are basically, this is a cartoon because there's variations of this issue depending on how you measure things, commonly called, for example, the cusp core problem or the too big to fail problem. These are closely related. There's other slight variations of this that people have discussed in the literature, but the general idea is if you take a pure gravity-only simulation, a very robust result for the naive vanilla cold dark matter model is that your dark matter halos, after they virialize, have, on average, Navarro-Frank-White type profiles, meaning that the dark matter density obeys a power law that at the center, density goes like r to the minus 1, basically. It has a cusp, a divergent slope. But qualitatively, all these problems amount to the density of dark matter in the centers of these halos is lower than you would naively infer from the extrapolation of a Navarro-Frank-White profile. The cusp core problem refers specifically to claims observationally that this profile is shallower in slope, that it's more like a flat central profile instead of an r to the minus 1. Too big to fail is more of an integral version of that argument. It doesn't care what the slope of the profile is, it just says that the mass enclosed inside of this radius is smaller than what you would get from NFW profiles of the same objects. So they amount to the same thing. The density is too low. There's also a ton of problems with the properties of galaxies in these naive models where it's just gravity and cooling. They go way back. Galaxy morphologies and scaling relations, many people have pointed this out. So, here's one example of galaxy morphologies. It's always, you'll commonly hear people say that simulations can't produce thin galactic disks, and this has been a problem for a long time in this field. So we observe, not all galaxies certainly, but many galaxies that look like this, have these beautiful thin extended disks. And from a paper by Grant Robertson that I was on, this was considered a halfway decent disk around 2005, not so long ago. Still incredibly compact, incredibly bulgy compared to the observations. Many people have shown this. So these kinds of models give you rotation curves that are very steeply peaked in the center, which is another way of saying galaxies are much too dense. Consequence of that is that if you put them on the scaling relations We measure between galaxy rotation velocity and mass, i.e. the Tully-Fisher relation. They lie systematically offset substantially from the Tully-Fisher relation. They have the wrong sizes, which also indicates that they have too little angular momentum, so somehow all the angular momentum that you would expect the dark matter and the baryons to carry into the galaxy, you can calculate how much angular momentum the dark matter carries in, and the gravity-only simulation gets lost or isn't effectively in the galaxies at z0 in these simulations. And their star formation histories are all wrong. They basically turn all their mass into stars very early in the universe. They don't just turn it all into stars, they turn it into the stars as soon as they possibly can, at very high redshifts. Whereas something like the Milky Way has a star formation history empirically inferred that looks more like this pink line. It's basically been more or less constant, maybe weakly declining for the last 10 billion years, not a giant spike and then a rapid decline. So all of these problems, I'll argue, are related, but there's a long history of all these issues understanding more massive galaxies. So obviously this picture is incomplete, and it's been pointed out for decades that, of course, this misses a very fundamental piece of the picture, namely that stars are not passive actors in galaxy formation. You form stars and then they do stuff. You can't just treat them as point masses. They explode as supernovae. We know that. They shine. We know that too. And that radiation heats up the gas, it ionizes the gas, it photoelectrically heats the gas, it pushes on the gas. The radiation pressure from starlight is comparable to the gravitational binding force on the baryons in most galaxies. The energy released in supernova explosions is 10 times the gravitational binding energy of the gas in most galaxies. So clearly, these are not negligible processes. And we see famous examples like M82 where they're not being negligible. So this is M82, this is the stellar disk, and here you've got images of both hot gas from the X-rays and H-alpha showing sort of warm gas being expelled from the galactic center. This is material moving out at hundreds of kilometers a second from the galactic center with an outflow rate that's comparable to the rate at which material is being turned into stars in the first place. So as much material is being blown out of this galaxy as is actually turning into stars, it's being blown out at velocities comparable to the sort of circular gravitational velocities. So this is clearly important. It sort of closes this loop and means that we can't just treat this problem top down. And that's why it's so hard, fundamentally, is because these very small scales couple very strongly to very large scales. So this is an example. This is a simulation by Tom Bell of cosmic reionization, which is a great example of very small scales, fusion inside of stars, generating high-energy photons that cause a phase change of the entire intergalactic medium that then subsequently strongly affects galaxy formation, because any galaxy, any dark matter object whose escape velocity is much less than 10 kilometers a second can't capture baryons in an ionized universe effectively. And so it actually does unambiguously affect galaxy formation. So this is why this problem is hard. And people going back several decades pointed out that the baryons could be responsible for many, if not all, of these weird discrepancies on small scales. But it's been very hard to argue that they really do explain those discrepancies. It's always been, it's not impossible, but it's been very hard to sort of test the null hypothesis, so to speak. But that's changed a lot in the last decade, and particularly in the last 5 years or so. And I would argue that there are three breakthroughs that are all, in some sense, connected, not all directly connected, but that all connects to this. The first is what I alluded to at the very beginning, that we have a concordance cosmology, which really goes back a little more than 10 years now, but that's been a really critical aspect of the progress we've made in galaxy formation. That we have well-posed initial conditions and a reasonable list of ingredients, and even if we might debate the detailed nature of these ingredients, large-scale structure really has to look more or less like this. We have enough constraints and enough redshifts that you can't, massively order unity change where things are and when they form. So you actually have a pretty well-posed sort of initial and boundary value problem. And it also means that you don't have the uncertainty of, well, it could be that I'm modeling the baryons wrong, but it also could be that omega matter is 1, which, is a big uncertainty if you're trying to forward model things, and you give yourself those kinds of degrees of freedom in the models. So the uncertainties in the expansion history and large-scale structure formation history of the universe have gotten to the point where they're much smaller than the uncertainties in our treatment of things like a supernova explosion. The other thing that's happened is dramatic improvements in resolution, partly due to Moore's law, but actually also partly due to algorithmic improvements that have enabled us to really resolve qualitatively new phenomena in galaxy formation. So this is an example. This is just a plot of simulations of Milky Way mass galaxies, specifically focusing on that mass range, and showing their spatial resolution in parsecs and their mass resolution in solar masses. And you can argue a little bit about how you put, depending on the numerical method, different simulations on this plot, but I just want to show some qualitative points. So several simulations, including some relatively recent large volume simulations. These look really bad on this plot because they're simulating tens of thousands of galaxies, so it's not fair to them. But some of these are only simulating one galaxy. They zoom in, you play this game where you have a low resolution box and you concentrate all your resolution on one galaxy. But progress has, along this track, is kind of slow going, but there's been a lot of improvements. And I'm going to focus on the firework, but actually other groups have done similar things in the last couple of years. With sort of the original fire simulations in 2014, we were able to move here on this plot with what we're calling Fire 2 and the latte simulations, which is Andrew Wetzel's version of the Milky Way on fire, is up here. And we're now running simulations that we're calling triple latte that live up here in this diagram, simulating Milky Way mass galaxies with 800 solar mass resolution and sub-parsec spatial resolution in the dense star-forming gas. If you ask these arrows, if you basically look, ignore the illustrious origin point, it's sort of arbitrary, the origin point here. The lower arrow, if you actually ask about the timeline of when a lot of these simulations were run, the lower arrow is assuming nothing but Moore's law. Okay, you just increase the resolution with Moore's law. The pink arrow is showing the actual increase in the resolution in the state-of-the-art of the field. And we've beaten Moore's law by a factor of 100 in the last 5-10 years. And that's because of algorithmic advancements, new numerical methods for solving the hydrodynamic equations, more efficient parallelization schemes, domain decomposition, optimization on new types of hardware that have enabled a lot of progress in this area. Just wanted to emphasize that. But physically, that's important too, because it's enabled exploring a lot of new physics. So the reason, that's not just a point to brag about to numerical people. If you want to resolve individual molecular clouds, say in a galaxy simulation, you need to be vaguely in this quadrant of parameter space. If you want to resolve the scales on which cusps and cores appear in satellites of the Milky Way, you need to resolve the inner regions of small galaxies around a big Milky Way mass galaxy, so you need to be up here. If you want to resolve the cooling radii, the radii where an individual supernova remnant radiates most of its energy away, which you're going to argue that supernovae blow gas out of galaxies, might be really important for getting its dynamics right, you need to live up here. If you want to resolve ultra-faint dwarfs around a galaxy, you need to resolve their masses likewise. So there's a lot of the key physics for this problem that live in this sort of quadrant of parameter space that's really only become accessible, cosmologically speaking, recently. And the last breakthrough that's very closely related to resolution is new physics, or I put new in quotes because it's really the recognition by galaxy people of physics that star formation people knew was important for decades. And galaxy people only in the last sort of 5 or 10 years have broadly as a community realized that this can matter on very large scales. It's not just a problem to sort out in the interstellar medium, but it propagates up the effects of some of this physics to very large scales. So I'd say if I had to pick 3, I chose these 3 as I think the most important 3, although I think there's a lot more subtle points. One is that star formation is strongly clustered in both space and time. We know this unambiguously, observationally, that stars form in groups and clusters. They form in a spatially correlated way. I'm using clustered in the cosmology sense. They are statistically correlated. I'm going to avoid the question of how many of them form in clusters defined a specific way, like a globular. That's a different question. And they're also correlated in time. GMCs are short-lived. And this means that when they explode, their explosions are correlated, which means that things like supernovae overlapping and generating superbubbles are much more common than you get if you randomly distributed stars over a galaxy. We also know that molecular clouds in which stars are born are disrupted and efficiently destroyed by some combination of radiation from the stars and stellar winds before most of the supernovae actually explode. And this is again very important because it means when your supernovae explode, they aren't going off buried under a huge column of very dense material. If you ask what's the terminal velocity of a supernova explosion if it goes off in the protostellar core in which that star formed, it's like a kilometer a second. You're not going to generate galactic winds by superimposing a bunch of supernovae that go off under those conditions. You need them to be able to break out. And to do that, you need to clear the path to some extent before they explode. Also, the realization that the interstellar medium is strongly supersonically turbulent and that structures within it are highly transient and short-lived. So you have this sort of constant process of forming and destroying molecular clouds. It's been an important realization. The ISM is not a sort of steady-state pressure equilibrium structure with very long-lived star-forming objects that are there sort of semi-permanently. That really changes a lot of how you think about implementing things like how stars form in your simulation and how they eject material. And this is just an example to qualitatively illustrate this little loop that's been playing the whole time. It's a simulation of an individual molecular cloud from one of my students, Mike Grudig, who's been working on sort of sub-GMC scale star formation, which I think nicely illustrates several of these concepts. There's no supernovae exploding yet. This has all happened, or there's a couple of supernovae at 16 million years, but most of the supernovae actually haven't exploded by the time most of the cloud is dissociated by initial radiation. And when you go up in scale, just to illustrate this, because I'm going to make reference to it a lot, this makes a big difference. So these are simulations by Steffi Walsh of a little patch of the interstellar medium, where you're just looking edge on, and these are showing the density and the temperature, and I think on the right it's the column density just projected. And these are cosmological simulations of a Milky Way mass galaxy, where on the left we're comparing if supernovae explode in just the highest density regions, if they haven't destroyed their environments around them, what happens, versus if supernovae are both clustered and exploding in cleared environments. You can see the right-hand side generates vastly more outflowing material. And on the right, the important thing was simply, if we assume that material is ejected at some sort of slow, steady rate from galaxies, that's what this top panel assumes, then the intergalactic medium, this is a couple hundred, about a megaparsec on the side, the intergalactic medium is very smooth and boring, and if you treat it more explicitly, things get more explodey, and I'll come back to that and actually quantify what I mean there. Promise we'll come back to this point. Okay, so let's put this together. So the goal of this particular simulation project, and again, we're not unique in trying to do this right now in the galaxy formation community, but I'm biased and I'm going to just focus mostly on these results, is to sort of test the null hypothesis. And what do I mean by the null hypothesis? I mean, I'm going to combine the vanilla CDM, lambda CDM model, the standard cosmology. I'm going to treat the dark matter as a collisionless, non-relativistic fluid that interacts only via gravity. And I'm just going to put in known stellar physics, things that we know exist with at least the current best guess about what they do. So I put in the cooling physics and chemistry from about 10 Kelvin to 10 to the 10 Kelvin, just standard cooling tables. And then I say, I crank my resolution up. I say that when gas gets sufficiently dense and self-gravitating and hits my resolution limit, I assume some fraction of it turns into stars. And then I treat those stars like a standard IMF, standard stellar population. I just, in this case, use starburst 99 to just say, what's the supernova rate as a function of time for that stellar population? Just dump that energy in whenever those supernovae explode. What's the wind mass loss rate from OD and AGB winds? What's the spectra of the stars, and use that to compute the photoionization and photoelectric heating and radiation pressure they exert on the medium around them. And newer versions of these simulations also include other things we know are there, like magnetic fields, Spitzer-Brzezinski, conduction and viscosity. A newest iteration includes cosmic rays. Those are more uncertain because we don't really know the transport coefficients for the cosmic rays. So I treat those as more experimental. I'm not going to really talk about them in this talk. But this is what happens when you put that together. The previous image was showing a zoom in of a small dwarf galaxy. You can see the multi-phase structure. This is now a cosmological simulation of a Milky Way mass galaxy in formation. And this is the stars on the left and the gas on the right. And you can see at high redshifts, it's undergoing an incredibly violent growth where material, mostly cool material from the intergalactic medium, is falling in very strongly supersonically. The galaxy accretes rapidly, turns mass into stars very rapidly, and then those stars drive strong feedback episodes that eject gas violently into the intergalactic medium, tear apart these infalling streams, etc., and drive very violent outflows. And the galaxy in stars kind of looks like a mess, as you'd expect it to during that phase. Around redshift 1, this thing starts to form a hot, steady-state virialized halo and calms down. It has one last big burst at z of 0.7 that was triggered by a minor merger. It was about a 1 to 4 merger. And then it really settles after that. And it nicely forms a sort of steady-state disk. Basically, after this point, it starts to look like that old cartoon from the 70s, where the hot halo starts to cool sort of quasi-hydrostatically down to form a more and more extended disk that conserves angular momentum and builds up an extended thin disk in the gas, which then turns into an extended thin disk in the stars. So, at higher resolution still, this is what the last billion years of one of our Milky Way mass simulations looks like in the stars. This is just having fun and taking a little fly through. This galaxy happens to have a sort of LMC mass companion merge onto it. So we just zoom through that because it's cool. We'll go into the core of the galaxy and come back out. You can see at the sort of state-of-the-art resolution that you can really resolve a lot of the dynamical violence and mess that's happening in the center, but you can see, spiral arms with individual large dust complexes that reflect the locations of molecular clouds. You can see individual star clusters forming in the galaxy, as well as some satellite galaxies orbiting around it, and others that have been shredded into tidal tails. It's a little hard because the background's bright. If you look on the laptop or there's a lot of small tidal structure that's very low surface brightness, so we'll just say that the projector is reflecting surface brightness dimming and move this galaxy to a half or something. So you do this experiment, you can ask, the first thing you can ask is what's the mass function of the galaxy? Because that's the sort of zeroth order problem that arises from the simplest models. And you get something that looks reasonably good, which is kind of shocking considering that we haven't actually fine-tuned anything to get this result. This was just the dumbest thing of put it all in from stellar evolution models and just brute force the problem. Not try and come up with a clever, effective model for how galactic winds emerge, but just say I'm going to crank up the resolution until I just brute force resolve their emergence from supernova explosions. And when you do that, it starts to actually look reasonably good. So stellar mass versus dark matter halo mass, these lines are the observational constraints of the observational mean tracks, basically. And this dotted line is what you get if you just turn all the baryons into stars. And there might be some subtle differences in the scatter or the mean of these, but it's at sort of factor of 2 level, which is, again, pretty good considering the simplicity of the approach here. There's some discrepancy that starts to grow at the very highest masses, we think is because we haven't included AGN, so basically these galaxies have the classical cooling flow problem as you go to the most massive halos, which we think should be there, actually, given the physics that we put into these things. I said I'd come back to this, so here's what the intergalactic medium looks like. On the left is this simple model where for every star that forms, I assume that it blows out just a proportional mass of gas. And I don't resolve any of the structure in the interstellar medium. This is basically the state-of-the-art, a decade ago, simulation. And this is the newer simulation, where you can see that this burstiness generates strong outflows. And what you're looking at is actually the temperature field of the IGM, and you've got hot, fast-moving gas that shocks gas quite far out. And if you look at what this does to the star formation history of the galaxy, it's really dramatic. So what you're looking at is the star formation rate versus redshift of this particular galaxy. And the red line is what you get if there's no feedback, if stars are just passive actors. And basically, this is the problem I described earlier. This ramps up very quickly as the dark matter collapses into larger structures, and it's basically being exhausted as soon as it's getting dragged in by the dark matter. So it exhausts all its gas supply very early, and then it just peters out because it's exhausted all the gas at late times. Now, if I do this simple, really dumb toy model, where I just say, for every unit star I form, I throw out a proportional unit gas infinitely far into the intergalactic medium, I get, depending on exactly how I do it, this blue or this green line, which just renormalizes the red line, as it should. All I've done is say, effectively, for every unit mass that goes into stars, I delete another unit mass. So it's just a renormalization. It doesn't actually change the shape of this distribution. But when you do this more carefully, you get this black curve, and there's two dramatic differences here. One, of course, that's glaringly obvious, is it's really bursty at high redshifts, especially, it's a combination of this is high redshift, things are happening violently and rapidly in the universe, but also the progenitor of the Milky Way, these high redshifts, is a small dwarf galaxy that lives in a very shallow potential well, it can easily blow out material, and that's happening very quickly. But it also changes the shape. Even if you smooth out the spikes here, the shape has actually changed. This is basically flat or weakly rising over this time. And the reason is because, again, at high redshift, this is a small dwarf, it lives in a shallow potential well. It's easy for it to blow out material, so it blows out material more efficiently here. But a key realization that's accompanied all of these others that I mentioned is that when that material gets blown out, it's not being blown out at thousands of kilometers a second, or at least most of it's not. It might be being blown out at a few hundred kilometers a second, let's say. Well, what does that mean? Well, it means that if this whole superstructure that it lives in is going to collapse ultimately to form the Milky Way, it might get out of the little virial radius of this tiny progenitor halo at redshift 10, but it doesn't escape from the entire superstructure that will ultimately collapse and form the local group at redshift 0. It's trapped somewhere in the intergalactic medium, and when larger and larger structures collapse at later and later times, that material comes back. It gets recycled, and what that means is you transfer accretion onto the galaxy from high redshifts to low redshifts. You move everything downwards in time, and you shift everything accordingly. And that helps with all sorts of problems that I discussed earlier. We'll come to those in. But first, let's just talk about some very direct consequences of that bursty, explosive feedback. So many people have argued, in fact, the first papers go back decades, but it's sort of resurged in the last few years with the ability to directly resolve these things in these simulations, that if you have this violent, bursty star formation in small dwarf galaxies, you're constantly throwing out the baryons from the center, and then they fall back in and then you throw them out again. They're only 10% of the mass, you say, so they don't do much. Well, yeah, but a 10% perturbation to the mass repeated 1,000 times is a big deal, actually. That's going to matter. And it's going to matter for the gravitational orbits of the dark matter in the center of the galaxy. You have a dark matter particle on some orbit around the center, and suddenly a bunch of the mass just disappears. It gets blown out at hundreds of kilometers a second. Well, what's going to happen on average is that orbit's going to widen, basically, because it just suddenly sees less mass inside. And then if that gas spirals back in, it can actually puff out the orbits even further because it exchanges angular momentum by dynamical friction as it spirals back in. So you effectively transfer energy from the supernova explosions that are pushing the gas back out via gravitational interactions. The gas transfers that energy to the orbital energy of the dark matter, and you end up, pumping up the orbits of the dark matter consistently. Every time you iterate this loop, you pump up the orbits of the dark matter particles. And various people have shown this both in toy models and explicitly in the simulations. You can track the history of the particles and show us what they're doing. And qualitatively, what that does is it lowers the density of the dark matter at the center of the halo. So it gives you something like these observations. And I'll show you some quantitative examples at the very end of this talk But there's a series of papers from FIRE by Jose Yorbe, T.K. Chan, Coral Wheeler, but also by a number of other groups, Chris Brook, Andrew Ponson, Cinto, and others, demonstrating this. Karim al-Badri wrote a very nice paper following up on this to show not only does this perturb the dark matter, but of course if there's stars in the galaxy, the dark matter did what I said it did just because it's a random collisionless particle orbiting this system. If a star's there, it's going to do the same thing. It's going to get kicked around the same way. So the same perturbation acts on the stars, and every time you have a little burst of star formation, what this shows is just that you excite radial velocities in the gas and stars, basically, that are correlated. And what this does is it basically mixes up the positions of the stars in dwarf galaxies. This can actually do all sorts of interesting things if you care about the properties of dwarf galaxies. It imprints radial anisotropy on their orbits, which then affects in turn the kinematic estimates of their masses, but it also affects their age and metallicity gradients if you care about their stars. So this is just an example showing the age and metallicity of one of these dwarf galaxies, where the blue line shows if you put every star at the radius from the center of the galaxy where it formed originally, what that gradient would be. And the point is that galaxies grow inside out. When the galaxy was first forming at very high redshift, it was very small. So the oldest stars would live here, and they would be the most metal poor. But those stars have also been perturbed the most violently. They've survived the most cycles of all of this. So they've gotten kicked out to the largest radii dynamically, which means that your gradient flips from the blue line to the white line is what you actually measure at z of 0 based on the present day positions of the stars. The oldest stars end up on the outside, so you can flatten or even invert these gradients. And not only do we see that generically, qualitatively in dwarf galaxies, but you can even argue, as we get more data, that you can actually use these to specifically test whether or not indeed these baryonic effects were the things that drove the cores, because it's strongly correlated. If you want to build a bigger core, you have to have done more violence to the stellar orbits as well. Another interesting thing that falls out of this that I wish we had the foresight to really run with is some of these galaxies that undergo this process for a very long time end up incredibly puffy. And when Karim wrote his papers, we noticed a couple of our galaxies were like a few 10 to the 8, 10 to the 9 solar masses and had like 5 kiloparsec effective radii, and we were like, these are kind of weird. We won't make a big deal out of them because we're not that sure that those actually exist. We got to figure out if we really believe that they're real, but I mean, they're there, so we published them, but we didn't make a big deal out of it. And then people like Peter Van Dokkum made a big deal out of finding these ultra-diffuse galaxies in Coma and other nearby objects, and now more people are working on this and finding them in the field. Several were already known for a long time. But actually, both us and other groups using different codes have been finding consistently that this process produces a lot of these sort of extremely low surface brightness galaxies. These are on the same surface brightness and size scale, actually, these two galaxies. So, very fluffy is kind of normal, it seems. And I could go on, and I don't have enough time to go into detail, but similarly, because it's easy to blow material out of dwarfs, you suppress star formation in the small dwarfs around the Milky Way, and you find very naturally that the missing satellites problem solves itself, basically, that if you compare the number of satellites, is the satellite mass function explicitly resolved in the colored lines around a massive Milky Way mass halo. These are 3 different random Milky Way mass halos that we selected. I think it's just dumb luck that it just happens that one of them lies on the Milky Way and one of them lies pretty close to M31's observed satellite mass functions. I wouldn't read too much into that, that's just dumb luck. Shea Garrison Kimmel has run 14 more of these and is writing a paper more statistically comparing all of their mass functions. This is really just a combination of stellar feedback blowing material out, but also coupled to another baryonic effect that matters for this is the fact that when you have a big baryonic disk like the Milky Way galaxy, it also tidally disrupts a non-trivial number of structures around it because close to the disk the potential is much deeper than if it was dark matter only, so substructures that are on radial plunging orbits get tidally destroyed. and that accounts for about half of the effect. Feedback accounts for about the other half. Likewise, I already gave the cartoon illustrating cusp core. Here's the quantitative version in the too big to fail constraint. So the upper panel shows the circular velocity as a function of radius. In one of these simulations of the 10 most massive dark matter substructures, satellites around the galaxy, if we only included gravity, and notice that they're basically all rotating much faster, have much larger enclosed mass than the most massive Milky Way satellites. This is the too big to fail problem. It's just another way of saying they have too much mass enclosed. But then when you actually include all the baryonic physics, these rotation curves all drop down to these lines, and they basically scatter around exactly the same place. If anything, there's a couple of M31 very compact satellites. Famously, M33, for example, is pretty compact, and I actually don't think we have any that are as compact as that, which is an interesting question. It might be just statistics at this point. So, I said earlier that eventually things calm down. I just want to remind you of that. So as we move on, at high redshift everything was violent, but as we approach Z of 1, things start to calm down. You get the hot halo has formed now, and these last mergers finish up, and things start to accrete more gently onto this galaxy, and it starts to spin up and build a more extended disk. And these are a couple of papers that analyze these different regimes. Sasha Muratov looked at the sort of high redshift, what I'd call the feedback-dominated regime, where it's very violent and you're blowing stuff out, all the way down to this late times where you have a more gravity-dominated regime. And there's a combination of things happening. Accretion rates are slowing down into the galaxies. They're getting more massive, so they're exhausting their gas more efficiently. They're higher density, so it's harder for material to escape. So you're trapping more winds that might have otherwise escaped. All of these go in the same direction of making the galaxy sort of calmer, basically. And what you see is that that corresponds quantitatively to the buildup of the galactic disk, as well as other nice orderly properties of galaxies that we associate with their scaling relations. Like Cheng-Cheng Ma wrote a nice paper on showing how as you transition from this sort of exploding feedback-dominated phase to this gravity-dominated phase, you rapidly build up metallicity gradients very quickly in situ in the galaxy. And you build up a sort of thin, thick disk structure. I'm not going to walk through all the details here. The point is just these are stars in different age wedges. If you take their present day positions and ask how old are they, if you take the oldest stars, they're all in an extended halo today. And if you take them, where were they when they formed, it's a little lumpier, but they're very extended when they formed. And it's just that the galaxy has been settling down over time. So basically a lot of the halo and thick disk structure is not stuff that gets scattered out within disk. It's not that the galaxy was always thin and heated everything up to very hot orbits. It's that it's more that the galaxy has sort of cooled with time and transitioned into a thin disk mode. And you can test that in much more detail with future observations I'll mention in a second. You can see this more quantitatively in the angular momentum concept. This is a different paper by Karim El-Badri, looking at the emergence of things like the Tully-Fisher relation, the galaxy size-mass relation, all the different galaxy scaling laws that I mentioned. So this is the Tully-Fisher relation, rotation velocity versus mass for stellar mass, but he looked at baryonic mass and all the other variations of the Tully-Fisher relation, and basically by redshift 0, massive things live nicely on this. At higher redshift, you get a lot more contribution from random motions that you have to account for, but that's also consistent with observations. And the stellar and gas angular momenta agree pretty well with what we observe in these galaxies. So there's no angular momentum catastrophe anymore. Dwarfs have less angular momentum because they're basically thick, irregular, bursty, clumpy structures, and that transfers a lot of angular momentum away. So this is the ratio of the angular momentum in the galaxy, either in baryons or in gas and stars, compared to all the dark matter. So at high masses, it sort of converges to about 1. This is the specific angular momentum gradient mass. So it's saying that the picture that everything gets spun up the same and just conserves angular momentum works pretty well when you're in this calm, massive galaxy phase. In the explodey phase, it doesn't work so well, but that's fine, because those galaxies are very puffy. And so you get a nice picture where you have dwarfs that just look like smudges at very low masses, and around the peak of the efficiency of turning gas into stars in the galaxy mass function, you start to form nice, thin, rotationally dominated structures. I sometimes show this plot just to remind people that not all galaxies are actually thin disks. In fact, while a lot of the stars live at this peak around the Milky Way mass, so a lot of the stars are in thin disks, all the dwarfs are not disky. They're big, ugly things that are just smudgy or clumpy. Well, I think they're beautiful. You don't see them on as many Hubble posters. And then at the very highest masses, you start to exhaust your gas and build up bulges, again, we think by things merging with each other. That would be a whole other talk, so I'm not going to go too far above the peak of the mass function. But the point is that thin disks emerge. These are a couple of the Milky Way mass galaxies simulated face-on and edge-on. These are some whole local groups with a Milky Way Andromeda pair that have other companions around them. It's a little hard to see. One of the illustrations I showed earlier, I think the screen wasn't quite bright enough for my trick to work when I showed the illustration showing, there we go, that you get a Milky Way. Voila, it was actually one of the simulated galaxies looking at it from the inside. This is the real Milky Way. But it's getting not so bad, actually, in terms of at least qualitatively reproducing some of the features we see. And if you really want to push the quantitative detail, I encourage you to. So Robin Sanderson has been leading a project to synthesize these simulations into mock Gaia catalogs, where we're, for every star particle, draw stellar populations, do the reddening, et cetera, all self-consistently using the actual phase-space distributions of the stars to populate where the mock stars go. And these are all going to be public in like a week. And they're going to be hosted alongside, they're going to be hosted both on just Robin's website, you download them, but they're also going to be hosted alongside the Gaia data at IPAC and at CCA, and they'll be alongside the public DR2 data, and they're in identical formats. And we're happy for feedback. We're trying to make it as easy as possible for people to just cross-compare the stellar populations in these galaxies with the real populations in the Milky Way. Of course, these aren't specifically designed to be exactly copies of the Milky Way, but for doing things like understanding, how well can you recover the structure of the galaxy, and are certain statistical properties consistent, I think this will be a really powerful tool. So you can go through heaps of galaxy scaling relations. I won't, because I'm running very low on time. But I just want to mention in the last couple minutes, a couple other problems that I didn't go into in detail, and then a couple other variations of dark matter and what they do or don't do. So other problems, there's been a lot of other potential small-scale problems. I didn't talk about them because they're either essentially the same as ones I discussed, or they're, I think, not as compelling. There's claims that CDM has difficulty reproducing the diversity of shapes of rotation curves, but in fact, the fact that baryons so violently rearrange the rotation curves actually produces plenty of diversity. Many people have shown that. There's also been the recent claims of the radial acceleration relation, which is what's plotted here, where you basically are plotting every point of a rotation curve on its own correlation, like a 2D baryonic Tully-Fisher relation. Coral Wheeler has a nice paper showing that, basically, if you reproduce the baryonic Tully-Fisher relation, there's no fundamentally new information content in this paper, or in this other relation, just from an empirical point of view. And so it's really the same problem. There's been a lot of discussion about planes of satellites around the Milky Way. I think there's a lot of debate still about how real these are as a statistical effect, but there's been multiple people showing that if you select from the simulations the same way the observational planes are selected, you can find consistent structures. There's an old argument about the globular clusters in fornax, and they should have all spiraled into the center. This is another variation of the cusp core problem. It's just that if you make the density of fornax's dark matter a little bit less dense than NFW, then the dynamical friction time gets much longer, and there's no issue. And it happens that fornax sits sort of at the stellar mass where you expect core formation to be most efficient, which I'll show in a second. There's also some claims of the most massive galaxy clusters, exhibiting weird dark matter profiles, but those are, I don't think, actually surprising, and they're also baryon dominated, so I'm happy to talk about them offline. So where do we go next? And this is where I wanted to mention briefly in my last couple minutes the other models we've explored for dark matter. So this isn't saying that you can't see differences between CDM and other dark matter models. The problem is it pushes the mass scale really low, where you would start to see differences in things like dynamics. So These are plots of the mass profile in dark matter only in dashed lines, and runs with all the physics in white lines of the dark matter mass profile. And you see that, and this number here is the mass in stars in the galaxy. So for a 10 to the 7 solar mass galaxy, you have a very big core. For a few 10 to the 6, you have a modest core. By the time you get down to a few 10 to the 5 in stars, you have almost no core. And you can actually understand this very simply. This is, showing this for a large sample as a function of the stellar mass to halo mass ratio, which for low mass galaxies, these are basically very small dwarfs. These are Milky Way mass galaxies. This curve here is going from no core, very strong core, to basically no core in the lowest mass galaxies. And what's happening in the lowest mass galaxies is very simple. You can convince yourself this just from an energetic argument. They form so few stars that there isn't, even if you transfer all of that energy through the supernova pushing the gas around and the gas gravitationally interacting with the dark matter, they don't have the ability to that significantly perturb the dark matter. They can't have gone through too many episodes of this because there just aren't enough stars there to power it. So if you can get to mass profiles of ultra-faint dwarfs, there's just energetically no way to do it, order of magnitude even, from stellar feedback stirring these things around. But of course, this is hard to do because it requires you measure kinematics in a galaxy that has, less than 10,000 stars total. So I apologize. You can convince yourself by running other dark matter models that then you would see differences. So we've actually run simulations with things like self-interacting dark matter with relatively large scattering cross-sections, a barn per GeV, warm dark matter with a few keV, fuzzy dark matter, which people are calling these ultralight scalar field models motivated by axions, but taking it crazy light, like 10 to the minus 22 eV, where the de Broglie wavelength gets to like a kpc, or even some of the models where the dark matter is primordial black holes at 30 solar masses or so. Interestingly, all 4 of these classes of models with these sort of canonical parameters you see in the literature end up being very similar for the galaxy properties I've described, in that they basically all produce kpc or sub-kpc scale lowering of the density of the dark matter structures. And in principle, if you got to really small galaxies, you could see that where you wouldn't see it in CDM, but it's going to be really hard. You could also see some differences in the satellites of satellites, because they're basically probing the very, very tiny end of the dark matter mass spectrum or the power spectrum. But it's really hard. And moreover, one of the interesting things, so running simulations with all of those dark matter models, all the baryonic stuff, if you ask what about the scaling relations of the galaxies, what about the shapes of the H1 rotation curves and how they relate to where the stars are, what about their star formation histories, what about the Tully-Fisher relation, none of that changes. If they move along those scaling relations. So these are runs with warm dark matter and cold dark matter, self-interacting dark matter, warm dark matter again. And again, these are pushing the limits of what's allowed. I'm talking, a couple keV warm dark matter, barn per GeV self-interacting dark matter. And to the extent that you perturb the star formation histories and the masses and the rotation velocities, the statement here is fundamentally that the baryons regulate what the baryons do. And so these scaling relations tell you about how baryons self-regulate themselves in their own arrangement inside a galaxy. They can be useful as tracers of things like the mass profile, and that's why I said there's still some hope at very low masses. But actually a lot of these things that people canonically said, oh, if we just made the dark matter fuzzier, it would make disk formation easier. That's just not true, actually. The scaling relations are basically insensitive to all these dark matter model variations, as far as we and other groups have been able to test in this newer generation of models. It was really, you saw more dramatic effects before because you were ignoring the amount of violence that the baryons actually did to themselves in the form of supernovae and things like that. So there's lots of directions to go in the future. I'm not going to read this slide. These are all sorts of new physics we're exploring, but most of these physics are geared towards understanding things about plasma physics, star formation, black hole formation in galaxies. The challenge going forward on the dark matter side, I think, is really, while galaxy and star formation have seen tremendous progress, this sort of null dark matter hypothesis remains a depressingly good fit from my point of view to the current observations. It's much more exciting if we'd really seen a breakdown that demanded new physics. It's not to say that there can't be new physics hiding there, but It's going to be very difficult to see, and especially very difficult to convince yourself that it's genuinely new dark matter physics. So, I end with a question: have we reached the end of being able to use galaxies and gravitational dynamics as a probe of dark matter? I don't know. I think certainly there's a call to explore model space that isn't motivated by this, let's make things fluffier at 1 kpc scale that has driven so much of the model building in the last couple decades. But I think, it's an unclear horizon in this field. So thank you very much.
Thank you very much, Bill. That was terrific. Questions? Carlos and then Ellen.
It's fantastic. But so, what about the rate of supernova explosion? Is that something that is established or something that we put in order?
So so in here we put it in at, according to some standard stellar evolution model, and those are uncertain in terms of the overall supernova rate. Those are calibrated to match the observed supernova rates. And I'd say easily you could put in a factor of a couple uncertainty in those, which would shift a lot of these masses by a factor of 2, roughly. If you make twice as many supernovae per unit mass form, you'll blow out more stuff, so you'll form fewer stars. So anything at the factor of 2 level is sort of fudgy in this stellar evolution way. Also, things like the effects of binarity on the energetics and stuff like that are also very significant at that level. And I think that's actually where a lot of the interesting sort of galaxy formation questions are diving into that. Like you can actually, one thing I didn't mention, you can actually have one failure of these models that's very obvious is that if you actually look in more detailed abundance space, we used a more than a decade-old model for the 1A rates, and it's missing a very early prompt population, and that just really messes with your abundances. The alpha to iron ratios are just systematically biased, and using a more modern sort of 1/T 1A prompt 1A rate distribution remedies that, but it doesn't really change any of the dynamics.
So my group has worked mostly with different cosmic ray transport models. And what we find is most effective in suppressing star formation is actually not driving a wind, but puffing up the disk. So if you think of a continuum where at one end the cosmic rays are so smothered by matter that they can't do anything, and at the other they're so mobile that they just leave by themselves, then the optimal is somewhere in between where they can prevent the gas from becoming dense, but not necessarily drive wind. And I wonder if you've seen anything similar in your more general forms of feedback.
We've seen, certainly qualitatively, some things like that with other forms of feedback as well, like radiative feedback can provide a similar role. And actually some of the more recent experiments we've been doing with cosmic rays treated very simplistically, and as is common in the galaxy scale simulations, you just treat it as a single ultra relativistic fluid, etc. We've seen some similar things. If you have the right diffusion coefficients, for example, you can get that sort of sweet spot. I think, I'd actually be curious your take on this, because you've obviously thought much more about this than I have, but one thing that was, if you want to hit that sweet spot, I don't think it qualitatively changes this story, but it is potentially important in its own right and can significantly affect the details of the star formation histories. But if you want to hit that sweet spot, what you end up with naively is a relatively large gamma ray flux predicted coming out of these systems. And the claim, there's this a couple of papers that claim that like the LMC and the SMC, for example, have very low gamma ray fluxes compared to what you would expect from the, they're a factor of 200 below the calorimetric limit. You take their supernova rates and turn that into expected gamma ray flux from hadronic losses. I don't know how to reconcile those. It seems like the gamma rays, or the cosmic rays, must be streaming very effectively out of those systems. But again, you've thought about this a lot more than that, I think. So.
If there's time, I'd love to talk about it.
Okay, great.
Yes, I did. I was curious about the star formation rate, which Carlos addressed, and the impact of the dust. You mentioned that there's a history of putting in the big scale effects, and where the resolution wasn't high enough in the past, just say magic happens here.
Yeah.
So I'm just wondering if the physics of dust has anything that would modify this, or if it's just, it's all such rapid timescales that the burstiness you were talking about gives you, dust, gives you gas.
Good question. I think it's, I'm of two minds because I think it's hard for the dust microphysics to sort of qualitatively change this picture, but I've actually gotten very interested in the dust microphysics, and with postdoc John O'Square, we recently wrote a series of papers on a bunch of new instabilities when you have dust trying to be accelerated through gas, like in the ISM, or if you want to use, if radiation pressure is accelerating winds, either in the atmospheres of cool stars or in star-forming regions, or in the AGN Taurus, for example, which are all feedback mechanisms that people have talked about and we attempt to include in these simulations. Here we ignore, on a microphysical scale, the fact that the dust isn't exactly dynamically coupled to the gas. That, we treat the dust as locked onto the metals in these simulations, but really the dust can drift through and it's aerodynamically coupled through Lorentz forces, et cetera, to the gas. And if you do that, there's a lot of unique instabilities that occur when you try and lift an atmosphere with radiation pressure, say on dust, that can actually drive dust clumping and filaments and all sorts of microstructure to the dust. And I think it's a really interesting question. I think it could strongly affect the efficiency even on large scales of radiative feedback, and it could affect significantly how efficient dust formation and destruction are in supernova explosions. I think that the integrated effect of that in turn on how much supernovae do to the galaxy as a whole is not going to be order of magnitude. It'll be smaller. But to actually interpret some of the observations where we need to deal with the dust very directly, or where the dust is our diagnostic, this could be very important.
And what about the star formation rate? Can you assume that the star formation rate is the same all over time? It's
So
just the total rate of stars, total rate of mass going into stars that changes because of the densities and so forth.
I guess I'm not quite sure what you're asking.
Distribution of masses of stars in the initial mass.
Oh, so the initial mass function. So that's a very good question. I've been working on that separately with another student, David Gusenyov, and this is just an assumption in these models that the IMF is universal. Is it? Great question. In Milky Way, it seems to be shockingly close to universal. This is the old problem of from the modeling side, getting an IMF that's universal enough. There's a claim that in the centers of the most massive ellipticals, there's evidence for the IMF becoming more bottom-heavy from indirect observations from stellar absorption line spectra. I guess being a good theorist, I've written papers arguing both sides of that. I have a paper arguing how you could do it from IMF variation, and how some models of turbulent fragmentation that produce the IMF that have been hot in the literature lately could produce this effect in the centers of massive ellipticals. The student, David, I wanted him to explore what this would do more broadly to galaxy formation, but rightly, before he did that, he carefully checked whether those models would overproduce the variation in the IMF in Milky Way clusters if you applied them inside our own galaxy. And they do rather severely. So he has actually gone through this exercise, and I'm not aware of a model that can predict IMF variation as large as is claimed in those galaxies, which is enough to matter for galaxy formation, factor of 2 or 3 in the mass to light ratio. Not order of magnitude, but enough to matter. But it's very hard to do that and survive the Milky Way constraints. So whether that means that those observations are being misinterpreted, and it could be something like we just don't understand cool dwarf spectra at weird abundance ratios, or whether it means that we're just not being creative enough in the IMF models, I don't know. It's the state.
So one more question after.
You mentioned that black holes are still to come.
Yeah.
I'm wondering the M sigma relation then, would that mean that you'd expect some effects on halo that are not yet included, or that you wouldn't expect them, and it's really that the halo affects the black hole? Do you have anything to say about that?
Yeah, so the simple argument that many people have made is if you take the M sigma relation and use it to estimate the sort of energy input, assuming some arbitrary constant efficiency of the black hole into either the ISM or the halo, what it leads you to is the idea that it's hard to avoid the black holes potentially being very important in the massive galaxies, but they're unlikely to be the dominant drivers in the low mass galaxies. They might very briefly, if they light up in a low mass galaxy, have a big effect, but integrated over cosmic time, they're just, there are relatively few big black holes that we're aware of in very low mass galaxies. But I think it makes it hard to avoid, the standard conclusion is if you get a fraction of a percent of the radiated energy coupling to the gas, it can do a lot dynamically in massive halos. And I think there's more and more evidence that both sort of quasar feedback, but also low luminosity, AGN, radio jets, etc., do a lot to galactic halos. So it's something that's very much under active development. As you're well aware, the biggest challenge is, with stars, you have a well-defined starting point. Stellar evolution has its uncertainties, but we can say, I'm just going to put in for this stellar population the supernova rate, the spectra as a function of time, and then just do the calculation. We obviously don't have that equivalent for supermassive black holes of population models at that level.
So I have 2 questions.
One question. Otherwise, the students don't get a chance.
All right.
You want me to flip a coin for you?
All right, then I'll just ask, most of the baryonic mass lies outside of the galaxies.
Yeah.
So you demonstrated a lot of successes. What about the general halo gas properties? How well does the high resolution solution can reproduce the observations?
Yeah, so let me very quickly, there's, sorry, I have too many bonus slides. Here's an example where things are getting reasonable with these models. So this is work by Cameron Hummels showing the, basically compared to the COS observations, but there's a lot of other observations around L-star galaxies of magnesium-2 absorbers and O6 absorbers. This is the points are column densities observed at different impact parameters. This is impact parameter in kiloparsecs, sorry. And these different contours are different mass resolution, basically. So this is in solar masses, what the mass resolution is. So as the mass resolution has gotten better, what you see is these are marching up, basically. And they're getting pretty close to the observations at the highest resolutions that we're able to resolve. And preliminary work suggests this is primarily being driven by, not actually, for the O6, it's not so much resolving small structures in the circumgalactic medium. The O6 clouds are pretty fluffy. It's mostly resolving the ejection of the oxygen from the galaxy. Particularly in massive galaxies, a lot of the O6 is coming out from venting of supernova ejecta in the hot phase, and it's just hard to resolve that. It's hard to resolve venting of hot gas out of the disk. The thing that nobody can resolve or explain in these large-scale, large-volume simulations are the cold ions with very high column at large impact parameter. So these would imply the highest end. This is 100 kiloparsecs away from the galaxy, and these column densities are nearly DLA-like in some of the most extreme examples, and there's no satellite galaxies there at these impact parameters. So the most popular models involve, for these cooler ions, a sort of mist of extremely small scale, like people talk about 10th of a parsec out in the diffuse circumgalactic medium, little raindrops, essentially, or mist of these cool ions. And to explore that, you can't hope to resolve that in this one-shot cosmological simulation. People are doing tricks, ourselves included, like, take a cosmological run and then just hyper-refine on one little patch of the circumgalactic medium and evolve that in isolation. So that's the state of these simulations.
So let's thank Phil once again.
Thank you.
So now we invite